Hi guys, this is the EdExcel AS Level Further Maths Paper 2 covering the Further Statistics 1 FS1 section, and it's from the June 2018 series. So in terms of the examiner report, there's a couple of things which we can say. First of all, calculators are expected to be used, but students must be able to write down mathematically what they are doing. Students are also advised to ensure they read the questions carefully, as far too many marks are lost by not answering the given question. That's actually quite important. Calculators are permitted and you can pick up marks quite easily on your calculator. Question 1. A researcher is investigating the distribution of orchids in a field. He believes that the Poisson distribution with a mean of 1.75 may be a good model for the number of orchids in each square meter. He randomly selects 150 non-overlapping areas, each of 1 square meter, and counts the number of orchids present in each square. The results are recorded in the table below. So here we have the number of orchids in each square meter, and then here we have the number of squares. He calculates the expected frequencies as follows, and those are shown here. And for part A, we have to find the value of our giving it answer to 2 decimal places. So what we can do then is, if we construct a table for part A, so what we can do is we can let x be the number of orchids in each square meter. So we have numbers going from 0 to 5 and then more than 5. Okay, so we have 0, 1, 2, 3, 4, 5, and then more than 5. Okay, and with this we can find out the probabilities that x equals xi. Let's just write that down. We have here the probability that x equals xi. And of course it would follow that from here x follows a Poisson distribution with mean 1.75. So we have x which follows a Poisson distribution with mean 1.75, and we can calculate the various probabilities using our calculator. So go to the menu, then the distribution section, we have a Poisson PD list. So enter in the numbers 0, 1, 2, 3, 4, 5. Our mean is 1.75, and calculating the probabilities, we have here 0.1738 to 4 decimal places, 0.3041, then we have 0.2661, then we have 0.1552, and then we have 0.0679, and then we have 0.0238. And to figure out this last probability, what we can do is multiply, we can do 1 minus all of these. So first thing, let's store all these into our calculator. So we can store this in A, we can then store this in B, store this in C, store this in D, store this in E, and then we can store this in F. Okay, so 1 minus those, so we have 1 minus this first one, minus this, minus this, minus this, minus this, and then minus this. So we end up with here 0.0091, and we can now record the observed values. Those are in this column here. So if we record those in, we have the observed values, or I, being 30, 42, 35, 26, 11, 6, and then 0. And we can now find out the expected values by multiplying these values by the value that was told to us in the question, which is 150. So we can now find out the expected values. So we have over here 150 times by A, which is 26.07. We'll give it to 2 decimal places. Then we have A times by B, that's 45.62. And then we have 150 times by C, that gives C 39.91. And then we have 150 times by D, that gives the 23.28. Okay. And then we have 150 times by E, which is 10.19. And then we have 150 times by F, which is 3.57. And for the last one, we have over here, well, if we work that bit we worked out before, so 1 minus A minus B minus C minus D minus E minus F, and then if we times this by 150, we come out with 1.37 to 2 decimal places. Okay, so therefore, hopefully you can see R is equal to 1.37. Okay, now for part B, the researcher will test at the 5% level of significance whether or not the data can be modelled by a Poisson distribution with mean 1.75. So we have to state clearly the hypotheses required to test whether or not this Poisson distribution is a suitable model for these data. Well, we have the following hypotheses. So H0, this Poisson model is a suitable model, and for H1, this Poisson model is not a suitable model. Of course, H0 and H1, those are the null and alternate hypotheses respectively. Now for part C, the test statistic for this is 2.0, and the number of degrees of freedom to be used is 4. We have to explain fully why there are 4 degrees of freedom. Well, the first thing you need to recognize from here, of course, we know that R is equal to 1.37. Because over here the expected values are less than 5 for these last two, we would have to combine all 3 of these. I'll show you what I mean. We have the 1.37 plus the 3.57, that would be 4.94, still less than 5, so we combine it with this one over here, so we add on the 10.19. So we come out with 15.13. We'd have to combine these last three. Let's quickly do that. So what we can say then from here is we see that the expected values are less than 5, as we've just discussed, for these two, and adding them up, combining them, we still have something which is less than 5, so we have to combine the last three cells. And doing that, we come out with these over here. Notice, combining the last three, we're now looking at where x is greater or equal to 4, so we have 4, 5 and greater than 5, which is the same as greater or equal to 4. So the observed value would be 11 plus 6 plus 0, which is 17, and the expected values 10.19 plus 3.57 plus 1.37, we just said that was 15.13. Okay, now when we come to talk about the degrees of freedom, that's equal to the number of cells minus 1. And we do this if the mean over here is not estimated, so is not estimated by calculation. Okay, and we see that this value of 1.75 is not estimated by calculation. We weren't told that we calculated this 1.75, so we can assume that we estimated this value not by calculation. Okay, hopefully that makes sense. Now, the number of cells we have 1, 2, 3, 4, 5 cells over here. So we have 5 minus 1, which is equal to 4. So therefore, the degrees of freedom would be 4. Okay? Now for part D, stating your critical value clearly, we have to determine whether or not these data support the researcher's belief. Well, what we need to do is find out the critical value. So for part D, finding out the critical value, we have 4 degrees of freedom. We're testing at the 5% level of significance. 5% of course is the same as 0.05. So going to our formula book, we need to go to the tables, and going to the tables we have 4 degrees of freedom. Let's just highlight this. We have 4 degrees of freedom. We're looking at, sorry, this is Poisson. We want the this one, so we want 4 degrees of freedom. We're looking at 5%, so that's 0.05, and the corresponding value, you'd find that to be 9.488. So we have 9.488. Okay, so if we draw a quick diagram to illustrate this, we have our critical region here, and our critical value, that would be 9.488. Here of course is where we reject H0, and here is where we accept H0, and we got a value of 2, so the 2 was calculated over here. So the 2 obviously is less than this 9.48 etc. So we have 2 over here, and therefore we do not reject the null hypothesis, so we can see that we accept H0, and because of that we can conclude the following. So we can conclude that the researcher's belief is supported, and that is that there is evidence that this Poisson model is a good model for for the number of orchids in each square meter. Now for part E of the question, the researcher works in another field where the number of orchids in each square meter is known to have a Poisson distribution with mean 1.5. He randomly selects 20 non-overlapping areas, each of 1 square meter, in this second field, and counts the number of orchids present in each square. Using a Poisson approximation, we have to show that the probability that he finds at least 1 square with exactly 6 orchids in it is 0.506 to 3 decimal places. Well, first of all, we can use our Poisson distribution to find out the probability of over here having exactly 6 orchids. Okay? And then we can use the binomial to create another Poisson distribution. Okay? And the reason we can do that is, hopefully you'll find that when we do use the binomial, if the mean is approximately equal to the variance, then we can use the Poisson approximation. So with this new model, for part E of the question, we have R, which is modelled with a Poisson distribution with mean 1.5. So the probability that R is equal to 6, we can find this out. So if we go to the distribution section, we have a Poisson PD variable, x is equal to 6, the mean is equal to 1.5. So we end up with a value of 3.529, etc., times 10 to the minus 3. We'll store this in A. Okay? So, having said that, we can now create a binomial distribution with parameters 200 and probability being 3.529, etc., times 10 to the minus 3. Now, why can we do that? If you look over here, what you'd find over here is he selects 200 non-overlapping areas, so that suggests to us that each selection is independent of each other. So we can use a binomial distribution just based on the fact that we have a non-overlapping areas. So with this binomial distribution, we can find out the mean from here, and if the mean is close to the variance, we can create another Poisson model to approximate this, okay? And to find this probability over here, this probability is just the probability of selecting exactly 6 orchids, okay? And we want to find at least 1 square with exactly 6 orchids. So this over here simply is what we have over here. Okay, so the mean, that's equal to NP, and that's in the formula book somewhere, if I'm not mistaken. So if you go to the formula book under the statistics section, that's given in some sort of table here. So the mean is here and the variance is over here. So the mean is equal to NP, so we have 200 times by 3.529, etc., times 10 to the minus 3. So if we work this out, we have 200 times by A, which is 0.7059, etc. So we have 0.7059, etc. Let's store this value into B. Okay? So we can now find out the variance the variance is equal to NP lots of 1 minus P. So we have 200 times by 3.529 etc. times 10 to the minus 3 times by 1 minus 3.529 etc. times 10 to the minus 3. And working out the variance, we have 200 times by A times by 1 minus A, which is 0.7035 etc. So we have 0.7035 etc. And because the mean is approximately equal to the variance, we can model this binomial distribution with a Poisson distribution. So because the mean is approximately equal to the variance, we can therefore approximate the binomial as a Poisson distribution. Okay, so in other words, we have y follows a Poisson distribution with mean 0.7059 etc. from here. And we're looking at, if you go back to the question, the probability that he finds at least one square. So we're looking at over here the probability that we have at least one, as shown here. So this comes from here. So he has at least one square. That's what we want to find. And for this, obviously, we'd have to use the cumulative Poisson. So this is the same as 1 minus the probability that x is equal to 0. So we have 1 minus, how could I do this? So if we go back to the distribution, let's actually use Poisson PD instead. So we have x equaling 0, mean equaling b. So we end up with 1 minus 0.4936 etc. So we have 1 minus this, which is 0.5063 etc. So we have 0.506 to 3 decimal places. Okay. Question 1. This question was concerning the Poisson distribution and forming a chi-squared test with it. Now, this question proved to be one of the more difficult questions for the students. The question tests the students' knowledge of the Poisson distribution alongside hypothesis tests, which were clearly familiar to them, but their answers lacked the required detail. Part A was generally well answered. The most common error was to calculate the probability that x equals 5 times by 150 rather than doing 150 minus the sum of the other expected frequencies, and that's what I did over here somewhere. I did 1 minus the rest to find out this probability, then I multiplied by 150 to get this result here. Part B, that was stating the hypotheses. Clearly there's a lot said on that. The examiners said that they are not looking to see if the data can be modelled by a Poisson distribution, but specifically whether it can be modelled by a Poisson distribution with mean of 1.75. So this must be included in the hypotheses. Part C, we had to talk about why we had 4 degrees of freedom. This not only tested if the candidates knew how to calculate the degrees of freedom, but also if they understood the reason behind their calculation. The majority of students knew why they were combined, although a minority did not mention in some form that it needed to be at least 3 columns which were combined. Few students were able to explain why 1 was subtracted, and 1 was subtracted because lambda is not estimated by calculation. The most common reasons were because there is one constraint, or because that is the rule, rather than making reference to the fact that 2 totals have to agree, or that the mean had been given and not estimated. So that's what I put over here. The mean is not estimated. The next part of the question, weaker students who were not confident in how to calculate the degrees of freedom often started with the premise that there were 6 groups rather than 7, probably not realizing the first column was for 0 orchards. So that's talking about this one over here. In part D, students had clearly been trained to recognize that chi-squared distribution was required and were able to correctly state the value of 9.488, so you could find that from the tables. However, conclusions were very rarely in context, many simply referring to the data rather than the number of orchards. Part E of the question, this is a show that question, and many students did not make their method clear. The working should include the distributions being used as well as the methods. Most students clearly used the binomial distribution, even though the question asked them to use an approximation. Others got the 0.706 from here, and then went straight to the given answer with no indication that Poisson of the mean of 0.706 was the distribution being used. Okay. Question number 2. The number of heaters H bought during one day from warm-up supermarket can be modelled by a Poisson distribution with mean 0.7. For part A, we have to calculate the probability that H is greater or equal to 2. So for part A, quite straightforward. We have H which follows a Poisson distribution with mean 0.7. And we're looking at the probability that H is greater or equal to 2. So this is equal to 1 minus the probability that H is less than or equal to 1. So we have 1 minus, now we can find out what this value is over here by using the distribution section. Poisson cumulative with variable x is equal to 1 and lambda that's equal to 0.7. So we have 1 minus 0.844 etc., which is the same as, if we work that out, 1 minus that 0.155 etc. Part B. For part B, the number of heaters G bought during one day from Pumraw supermarket can be modelled by a Poisson distribution with mean 3, where G and H are independent. We have to show that the probability that a total of fewer than 4 heaters are bought from these 2 supermarkets in a day is 0.494 to 3 decimal places. So here we have G, which has a Poisson with a mean of 3. Now, because we're looking at the total, if we say that Y equals H plus G, we can see that from here that Y follows a Poisson with mean 0.7 plus the 3. We can add them up because we're finding the total and they're independent. So from here we can see that Y follows a Poisson with mean 3.7. Okay, so the reason we add up as we've done over here is because we're looking at the total, and we're seeing over here, well, we have to find the probability that we have fewer than 4 heaters. Okay, so what we're looking at over here is the probability that y is less than 4. Okay, and this is the same as this is the same as the probability that y is less than or equal to 3. So working this out on our calculator, so if we go back to the distribution section, we have 3 here and 3.7 here. So we end up with 0.494, etc. Part C, we have to calculate the probability that a total of fewer than 4 heaters are bought from these 2 supermarkets on at least 5 out of 6 randomly chosen days. So what we can do over here is use a binomial distribution. What we've done already is calculated the probability that we have fewer than 4 heaters. We have 6 days in total. Obviously each day is independent of each other, and we're looking at having at least 5. So what we can do over here then is say that K has a binomial distribution with parameters 6. We have 6 days in total, and the probability of obtaining fewer than 4, that would be 0.494, etc. And we're looking at the probability that K is greater or equal to 5. We can see that from what was mentioned over here on at least 5. Okay, so what this is the same as is 1 minus the probability that K is less than or equal to 4, so we can use our calculator. So let's store this into A, and if we go to the binomial CD, we have a variable x is equal to 4, n is equal to 6, and p, that's equal to A. So we have 1 minus 0.896, etc. So we have 1 minus that, which is 0.103, etc. Okay. Now for part D of the question, December was particularly cold. 2 days in December were selected at random, and the total number of heaters bought from these 2 supermarkets was found to be 14. We have to test whether or not the mean of the total number of heaters bought from these 2 supermarkets had increased. We have to use a 5% level of significance and state your hypotheses clearly. Okay, so for part D of the question, what we need to do over here first of all is we need to come up with a new Poisson distribution. Now we see over here that the mean for the total number of heaters, if I highlight that, the mean for the total number of heaters, that was the 3.7 over here, and we're testing whether this has increased or not. Okay, so first thing we need to do for part D is write down our hypotheses. We'll quickly do that now. So we have our null hypothesis, the mean hasn't changed, so we have lambda equaling 3.7, and our alternative hypothesis, we have lambda being greater than 3.7. That's the first thing to recognize. And if we come up with a new Poisson model, if you go back over here, we have to multiply by 2 our mean, okay? And the reason we do that is we're looking at the 2 supermarkets, okay? So perhaps if I highlight that, so we're looking at the 2 supermarkets, so what we'd have to do over here is multiply this mean by 2, okay? So we have J, which follows a Poisson distribution with parameter 7.4. Okay, hopefully that makes sense. We're testing at the 5% level of significance, so that's 0.05, and we're looking at over here so what we're looking at over here is J being greater or equal to 14, okay, because we're looking at rather it's not, we're looking at 2 days, okay, so that's why we multiply by 2, sorry, that was my mistake. And what we're doing over here is looking at if J is greater or equal to 14, because we're looking at the increase, if it's been increased, and we found that the total number was greater than 14, so we're looking at the increase, so we're looking at 14 or greater. So what we're doing over here is looking at the probability that J is greater or equal to 14, which of course is the same as 1 minus the probability that J is less than or equal to 13. So let's just actually highlight that in a different color. So that bit comes from here, and we're looking at if it's increased or not. So with that, we can calculate what this is. So we have 1 minus, so if you go back to the calculator, back to the distribution section, Poisson cumulative, we have 13 and 7.4. So we have 1 minus 0.980, etc. So 1 minus this, we end up with 0.0195, etc. And this 0.0195, etc., that's less than this 5%. And because of that, we have to reject H0. Okay? And therefore, we have the following conclusion. So there's evidence at the 5% level of significance that the number of heaters purchased in total from the 2 supermarkets has increased. Okay? For question 2, we were looking at hypotheses test. This question was actually quite accessible for many students. Parts A to C were well answered. The most common error in part B was to not include the distribution used to obtain the final answer, and in part C to use the Poisson distribution rather than a binomial distribution. So I think it was quite obvious that for part B you had to add, because we were talking about the total, and for part C we had to use a binomial because choosing each trial is independent. For part D of the question, the hypotheses were generally stated with the correct parameter, although a minority of students tried to write them in words. There was no need. The most common errors appeared in the calculation, where a common error was to use a mean of 3.7 or to calculate the probability that x equals 14. You don't need to do that because we had to multiply by 2 because we're talking about 2 days in December. Pleasingly, conclusions were generally given in context of this question. It's actually quite important. Whenever you give your conclusions, make sure that it's in context. Question number 3. A fair 6-sided black die has faces numbered 1, 2, 2, 3, 3 and 4. The random variable b represents the score when the black die is rolled. We have to write down the value of the expected value of b. Well, part here, that's quite straightforward. Hopefully you can see that the mean, that's the same as the expected value of b. So we have 1 plus 2 plus 2 plus 3 plus 3 plus 4. Those are the number on the black die, and we divide this by 6 because it has 6 faces. Working this out, we get 2.5. For part B of the question, a white die has 6 faces numbered 1, 1, 2, 4, 5 and C, where C is greater than 5. The discrete random variable W represents the score when the white die is rolled and has probability distribution given over here. Greg and Nyla play a game with these dice. Greg throws the black die and Nyla throws the white die. Greg wins the game if he scores at least 2 or more than Nyla. Otherwise Greg loses. The probability of Greg winning the game is 1/6. We have to find the value of A and the value of B. Show you're working clearly. So this is actually a bit complicated. We've got G, and he has on his die 1, 2, 2, 3, 3, 4, and N, she has on her die 1, 1, 2, 4, 5 and C. Now we were told in the question that G wins the game if he scores at least 2 more than N. So if you look at the scores of N, G wins if he scores at least 2 more. Well, if N scores a 1, Greg will win if he scores at least 2 more than N. So if N scores 1 and G scores 3, G has 1. So actually let's write this down. So G wins, so Greg wins if N scores a 1 and G scores a 3. Now N can also score a 1 and G can score a 4, because remember we were told in the question that the score that G has must be at least 2 more than N. And next, if N scores a 2, then G can score a 4. Now for the rest of them, obviously if N scores a 4, there's nothing greater that G can get. If N scores 5, there's nothing greater than 5 over here. And obviously because C is greater than 5, because N is, if N scores C, then Greg can't score anything greater than that. So these are the only 3 options there are for Greg. Now let's write this down in terms of probabilities, and obviously this is where it gets a bit more complicated. Now remember, Greg, he is represented by the black die, and G and N is represented by the white one. So let's just put over here B and W. Okay, so the probability that Greg wins, well, that's equal to the probability of getting a white with 1 and the probability of getting a black with 3. Or we can have the probability of white being 1 and the probability that a black equaling 4. Or we can have the probability that a white is equal to 2 and the probability that a black is equal to 4. Sorry, what am I writing here? White equals 2 and black equals 4, yeah. And working all this out, what we have over here, the probability of winning a white one, that would be A plus B. So we have A plus B, lots of the probability of getting a black. So now there's that's the probability of black equaling 3, so there's 2 3s over here out of 6. So we multiply by 2/6, and then we have the probability of white equaling 1 again, that's A plus B. And then black equaling 4, well there's one black one, sorry there's 1 4 out of 6 in total, so we multiply this by 1/6, and then we have white equaling 2, so W equals 2, that would be A, and then we multiply this by black equaling 4, so we have 1 4 out of 6, so we multiply this by a 6th. So we have, what we have over here then is a third, lots of A plus B, plus 1/6, lots of 2A plus B. And the reason we have 2A, if I factorise out a 6th from here, we have 2A inside the bracket and a B as well. Now, we were told in the question that the probability that Greg wins, that's equal to 1/6, okay? So the probability, all this essentially is equal to 1/6. So we have 1/3 lots of A plus B plus 1/6 lots of 2A plus B equals 1/6. And that 1/6 is the probability of Greg winning. And if we multiply through by 6, we have 2 lots of A plus B, so we have 2A plus 2B plus 2A plus B equals 1. In conclusion, we see that we have 4A plus 3B equals 1. We'll call this equation 1. And we know that the sum of probabilities, that's equal to 1. Alright? So, because probability adds up to 1, adding all these together will get a total of 1. So we have A plus B. So we have A plus B plus A plus the 0.3 plus A plus B equals 1. In conclusion, we have here 3A plus 2B equals 0.7. We'll call this equation 2. And if we solve equation 1 and equation 2 simultaneously, doing that, well, let's just use our calculator. So solving those simultaneously, so we have a simultaneous equation with 2 unknowns. So we have 4, 3, 1, 3, 2, 0.7. We see that A is equal to 0.1 and B, that's equal to 0.2. Okay, So what we can now do, knowing that a is equal to 0.1 and b is equal to 0.2, let's fill all these values in again. So here we have a plus b, so we have 0.3 here, 0.1 here, we still have this 0.3, 0.1 here, and 0.2 here. So we found the values of a and b, and now for part C, the random variable x equals 2w minus 5, given that the expected value of x is equal to 2.6, we have to find the exact value of the variance of x. Well, what we can do with this is we can find out the expected value of w, and then we can multiply these together to find out what that is, to find out the value of c. And once we've done that, we can relate the w via x via the variance. So I'll explain what I mean. So for part C of the question, the expected value of x, remember x, that's equal to 2w minus 5. Okay, and we know that this expected value, let's grab a different colour here, this expected value, that's equal to 2.6. So we can rewrite this as 2 times by the expected value of w minus 5. And we have a table involving w's, so with that we can find out what c is. So this over here is equal to 2.6. Okay, and that's from what we were told in the question. And if we solve for the expected value of w, well, adding 5 to both sides, we have 2.6 plus 5, which is 7.6, and if I divide this by 2, the expected value of w is equal to 3.8. We might use that later on. Okay, so knowing the value of the expected value of w being 3.8, we can now find out what c is with that. So what we have then is the expected value of w equaling w lots of the probability that w is equal to w. Okay, so we have 3.8 over here. Again, sorry, if we do this in a different colour, we have this over here, the 3.8, and this is equal to w lots of these probabilities. So we have 1 lots of 0.3 plus 2 lots of 0.1 plus 4 lots of 0.3 plus 5 lots of 0.1 plus c lots of 0.2. And if we form an equation, hopefully you can see that we have 0.2c equals 1.6, and therefore c, that's equal to 8. So let's construct a new table. First of all, we know the expected value of w, and we can find out the expected value of w squared, and from that we can find out the expected value, the variance of w, and then we can find out from that the variance of x. So the expected value of w, for that we need to find out what w squared is. So let's construct the table again. So we have w squared, and the probability that w equals w. So with this, we have 1. So we have 1, 2, 4, 5, and 8. 1, w squared would be 1, 4, 16, 25, and 64. And probability that W equals W, we wrote these down in red before, so we'll write those down again. We have 0.3, 0.1, 0.3, 0.1 and 0.2. And from this we can find out the expected value of W squared. So this is equal to the sum of W squared times by the probability that W equals W. So we have 1 lots of 0.3 plus 4 lots of 0.1 plus 16 lots of 0.3 plus 25 lots of 0.1 plus 64 lots of 0.2. And if we work this out, we end up with 20.8. Okay, so with this we can find out the variance. So the variance of W, that's equal to the expected value of W squared minus the expected value of W all squared. So we've worked these out. We have 20.8 minus 3.8 all squared, which is 6.36 if you work that out on your calculator. Now we want to find the variance of x. So the variance of x, we know what x is. X is equal to 2w minus 5. So we have the variance of x equaling 2 squared times by the variance of w. We've just worked out what the variance of w is. So we have 4 times by 6.36, which is 25.44. So that's the variance of x. Question 3 was concerning discrete random variables. The majority of students were able to gain marks for part A. You just had to recognize that the expected value of B is equal to the mean, and you can find out the mean by adding up all the numbers and dividing by how many they are. Part B was a bit more challenging. Those who wrote down the ways in which Greg could win fared best, as they were able to attempt to find the probability in terms of A and B. So if you look over here, you can see that I listed the different ways Greg could win. So what I've just said, so those who wrote down the ways in which Greg could win fared best, as they were able to attempt to find the probability in terms of A and B. However, this was rarely seen. Most students tried to just write down the probability of Greg winning straight with little success. However, they usually managed to use the fact that the total of the probabilities must equal 1 in order to come up with this equation over here. Part C, where we had to find the variance of x, students used a mixture of methods to answer this. The majority of students knew the correct formula for the variance but did not check it was all in W or x. All too often they used the expected value of x squared minus the expected value of W all squared. Another common error was to find the expected value of x squared using the expected value of 2w minus 5. I think the way I did it was actually quite straightforward. Question number 4. Abram carried out a survey of 2 treatments for a plant fungus. The contingency table below shows the results of a survey of a random sample of 125 plants with the fungus. So we've got the outcome over here and then the treatment over here. Abram calculates the expected frequencies to carry out a suitable test. 7 of these are given in the partly completed table below over here. The value of the sum of the observed minus the expected all squared over the expected for the 7 given values is 8.28. So what they've done over here is 8 minus this all squared over this, plus 7 minus this all squared minus this, etc. And they've done that for each of these remaining 7. And we have to test at the 2 point 5% level of significance whether or not there is an association between the treatment of the plants and their survival. State your hypotheses and conclusion clearly. Well, our hypothesis, H0, there is no association between the treatment of the plants and their survival. H1, there is an association between the treatment of the plants and their survival. And the next thing we need to do, we need to know how to find out the expected value. That's equal to the row total times by the column total all over the grand total. Okay, so we divide this by the grand total. Okay, so first of all, finding out our rows and column totals. Well, 15 plus 8 plus 7, that would be 30. 16 plus 25 plus 14, that would be 55. 25 plus 10 plus 5, that's 40. 15 plus 16 plus 25, that's 56. 8 plus 25 plus 10, that would be 43. 7 plus 14 plus 5, that would be 26. And the total, that would be 125. Okay, so we have the 125 over here. Let's just box up. That's our grand total, and let's just box it over here. So here is our grand total. Okay, so for these values over here, we can find out the expected values. So we have here, if we work this out, we have 30 times by 56 over 125, which is 13.44. So we have here 13.44, and here we have 55 times by 56 divided by 125, which is 24.64. Okay, so what we can now do is find out the test statistics. So chi-squared, that's equal to the sum of the observed minus the expected, all squared, over the expected. So for the remaining 7, those are already calculated. So for the 2 that weren't calculated, we have 15 minus the 13.44 all squared over 13.44, and then we have 16 minus 24.64 all squared over the 24.64, and happily for us, for the remaining 7 that was calculated, it'd be 8.29. So working out the value of chi-squared, we have here 15 minus 13.44 all squared over 13.44 plus 16 minus 24.64 all squared over 24.64, and then we add on 8.29, so we come out with this value over here of 11.5006, etc. Now we can calculate the degrees of freedom for this contingency table. We have 3 rows, 3 columns, so the degrees of freedom, we have 3 minus 1, lots of 3 minus 1, which is 4. We're testing at the 2.5% level of significance, so we can find out from here, our critical value. So working this out, we'll have to go to the formula book. So if we go back down to what we have over here, we have 4 degrees of freedom. So let's just change the color. We have 4 degrees of freedom. We're testing at the 0.025% level of significance, and what you'd find is the critical value, that's 11.143. So drawing a quick diagram to illustrate all this. Sorry, let's draw it neatly. So we've got here our critical value of 11.143. Here is where we reject H0, and here is where we accept H0. And what we found is we got a value of 11.5006. So that is somewhere over here. So here we have 11.5006, etc. So what you can see over here is we reject H0. And what does this mean for our conclusion? We have the following conclusion. So there is an association between the treatment of plant and their survival. Okay, so that's the end of this paper. Question 4 was concerning contingency tables. It was clear from the candidate solution that they knew how to use a chi-square test on a contingency table. However, the most common error was having the hypotheses the wrong way around. The majority of students had little trouble in calculating the missing expected values, but a minority did not realize that the 8.29 over here was given in the question, so you don't need to write out the full working out, you just had to add on this, which represented the 7 missing values for this. What else could we say? And because of that, they lost unnecessary marks. Others worked out the observed squared over the expected for the 2 values, and then added this to the 8.29, which is incorrect.